Welcome to the new session on data envelopment analysis. In the previous session, using the graphical method as well as the linear programming optimization method, we saw how to identify efficient DMUs and inefficient DMUs. If you recall, efficient DMUs essentially fall on what was called as efficiency frontier, right? Efficiency frontier is the envelope. And all the efficient DMUs are the ones which have the objective function value of 1 after you solve the linear programming problem that we had seen in the last session. Now this session we are going to focus on inefficient DMUs, the DMUs that somehow did not find themselves on the efficiency frontier. Can we do something for them? Can we tell them what to do? So first of all, we will identification of these inefficient DMUs. We partially did that in the previous session. So very simple, the inefficient DMUs are the DMUs which are going to report an objective function value of less than 1 when you solve the linear programming problem for them. Now that you have identified the DMUs which are not efficient, can we do something for them? Can we tell them what to do? Can we prescribe something so that they can also move towards efficiency? So graphically speaking, essentially we are telling them a path towards the efficiency frontier. Right. So we have so just to summarize, essentially the graphical output as well as the optimization problem. Both are the data envelopment analysis methods. Even the graphical method was data envelopment analysis. The optimization problem formulation was also one of the formulations of DEA. This is there are other ways of formulating the optimization problem for DEA, but right now we have not discussed the details of those formulations. Right? Remember we had discussed something called BCC model, CCR model. So you can read about them on your own, but we have seen a basic optimization problem which when it is solved tells us which DMU is efficient and which DMU is not efficient. So essentially the inefficient DMUs are going to find themselves farther away from the efficiency frontier. Now we want to tell them what to do, right? How can these inefficient DMUs become efficient? Graphically speaking, as I said, the only way they can be called as efficient DMUs is when they move towards the efficiency frontier, right? So they should move themselves. Towards the frontier, and if they are sitting on that efficiency envelope, we are going to call even these DMUs as efficient DMUs. However, the movement towards the envelope or even towards the frontier is not vertical or horizontal, right? We'll come to that. I'll explain that in the next slide. But the movement of the inefficient DMUs towards the efficiency, that movement is neither vertical nor horizontal. Why is that? The reasons are once again technical. We have not gotten into the details of the economics of the data envelopment analysis. So a lot of things we have skipped. So there are things like scale efficiency, technical efficiency, pure technical efficiency. So SE is scale efficiency, TE is technical efficiency, PTE is pure technical efficiency. So there are a lot of concepts that we have not discussed. For example, we have not even discussed disposability of inputs and outputs. Typically that gets converted to what is called as CRS or constant return to scale, or VRS, which is variable return to scale. Now even VRS has been further classified as DRS, which is decreasing return of scale, IRS as increasing return of scale. All these are economic concepts which play a very important role in data envelopment analysis, but we have not discussed. That will be going further deeper into data envelopment analysis, and we have kept that part out of the scope for the current discussion. So summarizing, why is the movement of inefficient DMUs towards the envelope neither vertical nor horizontal? Well, it is not because of these concepts, because of scale efficiencies, because of CRS and so on, right? So let us not bring those in right now. Let us take that the movement towards envelope is going to be a slightly inclined plane. What do I mean by all this? What do I mean by all this? Recall. Let us go back to the simple example where we had two inputs. Remember the two inputs, the two input and one output case. What were the two inputs? The two inputs were, I think, budget and the team size. Those were the marketing and sales team. Hoping that more people you have in the team, hopefully you are able to achieve more sales. And what was the only output? The output was the sales achieved, right? For this simple example, I think we had kept the sales constant. So target, everybody was told that they need to generate a sale of 10 lakh INR, and then we gave them different budgets and different team sizes, right? So recall that the graphical output of the data for 5 DMUs looked something like this, right? Once again, the two inputs, budget was an input and team size was the another input. If you recall, we are not going to get into the solution again, but if you recall, DMUs 5, 2 and 3 turned out to be efficient, which essentially means that when we solve the linear programming problem for them, the objective function values for these 3 DMUs turned out to be 1. And we said 1 was the maximum efficiency you can get because we had put a constraint that nobody should get an efficiency more than 1, right? That was a constraint. So all the good ones will get an efficiency of 1. But as I had earlier mentioned, the focus of this session is not on the efficient DMUs. The focus of the focus of this session is actually on 1 and 4 DMUs 1 and 4, which have been found inefficient. And why are they inefficient? Because they are not on the red efficiency frontier. So now we have to give now we have to find a method to prescribe to 1 and 4 what to do, right? They are clearly sitting there asking us, well, I also want to become efficient. I also want I also want to be called as efficient. What should I do? Right? So they have to hit efficiency frontier. Only way I can call them efficient is when they are sitting on the efficiency envelope. So that's what I was saying. So the movement, let us move them. So I can move DMU 1 and say that, well, if it simply reduces the budget, right? If it simply reduces the budget, reduce the budget. You are currently spending something like 300,000, right? Reduce the budget to about 200,000, and I will call you efficient because you will be sitting here on the efficiency frontier, and I will call you efficient, right? Similarly, for DMU 4, I can say that, well, draw a vertical line. I can say that DMU 4 probably is, I don't exactly remember, but DMU 4 is having a marketing and sales team of about 10 people. You bring it down to 8 people and then you will hit that efficiency frontier. I'm not being exact here, probably I have to find out. But essentially, whatever number is the team size here, which is the intersection of this vertical line and the efficiency frontier, I will say move DMU 4 here, which means essentially keep the same budget, but only reduce the team size. So that is what I mean by this vertical or horizontal movement. Unfortunately, we don't recommend that in this method of DMU, right? The method that we are currently discussing. So we are not going to say either move horizontally so that you are sitting on the efficiency frontier, or you move vertically so that you are sitting on the efficiency frontier. But the idea is the same. I will call you efficient only if the DMU is found to be on the efficiency frontier. So we have to tell DMU 1 and 4 how to move towards the efficiency frontier. And what is the basic idea? We are going to draw a straight line starting from origin, and we are going to say that, join that with 1, and we are going to say that I want DMU number 1 to move in this direction, which is neither horizontal nor vertical. Okay, vertical movement would have been simply reducing the team size. Horizontal movement would have been simply reducing the budget. I don't want you to do either. I want you to move in the direction indicated by the blue line, Okay, so when you move the current input values to this new input value, so DMU1 is probably spending something like $300,000 in terms of 300,000 rupees in terms of budget. Probably it has a team size of 13 or something, right? It looks to be between 12 and 14. And now I am recommending that one moves in the direction of the blue line and hits the efficiency frontier here, right? Which probably means that it is somewhere, I don't know, so somewhere more than 200,000 rupees, but certainly lesser than 300,000. The team size definitely lesser than 13, but seems to be of the order of 10 or little less than 10. And once it moves here, I will call DMU1 also as efficient DMU. Okay. This point here, which is the end result of efficiency efforts by DMU1, right? So this point here on a two-dimensional coordinate system, this point here which represents the end result of the efficiency efforts on part of DMU, this is called Hypothetical Composite Unit, HCU. Hypothetical Composite Unit, right? So unit is just a decision making unit, right? We have been calling these as DMU, so that is not surprising. Why hypothetical? Hypothetical because it is not present in the data as of now. The coordinates of DMU1 are here. So what we are asking is a hypothetical scenario where DMU could be if it puts in enough efforts to move towards efficiency. So in that sense, it is only a hypothetical unit. The real DMU1 is sitting here. This HCU is only a hypothetical situation. We are imagining if DMU1 puts in enough efforts, probably it can call itself efficient if it moves towards this unit, this hypothetical unit. Now, why is this called composite? Let us hold on for a couple of slides to explain that, right? And there is a definite meaning for that also. That is the reason that this point is called hypothetical composite unit, and let us put a subscript 1 here. Just to say that it is a hypothetical composite unit for DMU1. Very similarly, what is our recommendation for DMU4? Again draw a straight line starting from 0. Right? I mean, the way I have drawn it doesn't look to be perfectly straight, but imagine that this is straight, right? So what is our prescription to DMU4? How should DMU4 become efficient? DMU4 should not become efficient only by reducing the team size. It should not become efficient only by reducing the budget. That would have been a horizontal movement. Right? Horizontal movement means reduction in the budget. Vertical movements means reduction in the team size. We don't want to recommend reduction of only one input. We want DMU4 to show reduction in both the inputs. So we want DMU4 to move in the direction of this blue line and hit the envelope here. We don't recommend DMU4 that it hits the envelope here. We don't recommend that. We want DMU4 to hit the envelope here, which is reduction in both budget as well as the team size. So just like we did for DMU1, this point here is going to be called hypothetical composite unit for DMU4. So this is our policy prescription for the inefficient DMUs. This is our policy prescription. So we will draw a line starting from origin starting from origin and connecting to the inefficient DMU, and the point of intersection of this line with the efficiency frontier is our recommended new position for the inefficient DMU. So we recommend that the DMU1 should move to HCU1, and we recommend that DMU4 should move to HCU4. This is the graphical explanation of what we are going to do now. Okay. So as this is just summarizing. So DMUs 1 and 4 are inefficient. So and they have to move. Essentially, move meaning reduce the inputs. Here, this is an example of 2 inputs and 1 output. So the only way the DMU can become efficient is to reduce the resources. Reduce the resources that it is consuming. Budget is the money that it is consuming. Team size is the people resource that it is consuming. Right. So reduce on both of these resources. Only then the DMU can move towards the frontier. Right. So when they hit the frontier, that intersection point, this intersection point, we have discussed this now, right? This intersection point is going to be called hypothetical composite unit. Hypothetical composite unit. And from the two-dimensional coordinate system, for this simple example, it's very easy for us to identify this, right? How do we do that? Now you already said what is this blue line? Blue line is the line joining origin and DMU4. Blue line is the line joining origin, which is coordinate 0, 0, and DMU4, and you know from data what is the coordinates of DMU4. You know the input, which is the budget as well as the team sizes for DMU4, right? You know this. So you know the coordinates of 4, you know the coordinate 0, 0. Therefore, you should be able to find the equation of the line which is passing through these 2 points, which is the blue line, right? We have drawn only a segment, but let us not get into technicalities. We know the equation of, we should know the equation of this blue line. Similarly, you know the coordinates of 2 because the DMU2, you know how much budget has it been allocated, you know how much team size has it been allocated. So, you know the coordinates of 2. Similarly, you know the coordinates of 3. You know the coordinates of 3. Therefore, the line joining 2 and 3 is this red segment. I'm calling it line segment. So yes, I'm making a slight error, but it's okay. For the point of for the purpose of explanation, you know what I'm saying. So imagine this as extended version, not only the segment, but you should be able to find the equation of this line which passes through 2 and 3. And therefore, HCU4, which is a point here, can then be identified as a point of intersection of these 2 lines, right? The blue line as well as the red line. The blue line as well as the red line. Okay. Now let me explain the last missing piece, which was the composite. Why is the point called hypothetical composite unit? We have explained hypothetical part because it's only hypothetical. We are only saying 4 could possibly move to HCU4 if it wants to be called as efficient. We know what a unit is. Unit is a decision making entity, DMU, right? Unit. What is this composite? We are going to now say that inefficient DMU4 can move towards efficiency, which is this point. Now we are going to argue that HCU4 is a composite essentially prepared from 2 and 3 because it is the intersection of the line, the blue line with the line passing through 2 and 3. So this HCU is composed of some elements of 2 and some elements of 3. Okay, that is why this is called composite unit. It is composed of some elements of 2 and some elements of 3. How is that? We will reveal that in couple of minutes. I hope so far we are doing all right. So we are arguing that this HCU1, HCU4 can be identified by simple geometry because HCU1 and HCU4 are essentially point of intersections of 2 lines, and the equations of these 2 lines we know already. So let us do that. Let us do that. Right. So this is the final. slightly better looking diagram which shows the hypothetical composite unit for 1 and hypothetical composite unit for 4. Okay. So how are we going to find HCU1 and HCU4? Let us do that for HCU1. Okay. So coordinates of DMU1 are 300,000 and 13, which means that to generate a revenue of to generate a sales of 10 lakh rupees, DMU1 consumes a budget of 3 lakhs, consumes a budget of 300,000, and it requires a sales team of 13 people. That is what the coordinates mean, right? Now, this HCU, the HCU for DMU1 is a combination of two efficient units, and we already identified what is the what will be the composite. What is the composition of this HCU? The composition of this HCU will be efficient unit 2 and efficient unit 5. Efficient unit 2 and efficient unit 5. Therefore, for inefficient DMU1, DMUs 2 and 5 are called the reference unit. They are called the reference unit. They are called the reference unit, and the combination of these two references will give you the coordinates of the hypothetical composite unit for DMU1. So, how are you going to find that? You are going to find that from point of intersection, right? And I leave that simple geometry to you. I will simply present the final result, and we can find that the hypothetical composite unit for DMU1 has coordinates of 2,37,540 and 10.3. Okay, so go back. So what is this HCU here? This HCU here is 237,540 and 10.3. So this is 237,540, and this vertical line here seems to indicate that it is right, some just about 10. Okay, what does that mean now? What does that mean in the context of our DMU? Currently, DMU1 is being inefficient because it is spending a budget of 3 lakhs and a team size of 13. It needs to bring it down, right? Inputs have to be consumed less if you want to be called efficient, right? There are only two ways that you can be called efficient. Either you produce more or you consume less. Those are the only two methods. Here we have fixed the output. Output is sales, and sales you have to achieve 10 lakh rupees of sales. So you really can't go in that direction. We are not going to propose that you increase your sales. So the only way we are going to recommend is to reduce your inputs. And what is our recommendation? We are saying that DMU1 will be called efficient if it spends a budget of about 2,37,000 and it has a team size of 10.3. Okay, which essentially means that DMU1, if it wants to be called as efficient, it needs to reduce its budget from current 300,000 to about 237,550. And it also needs to reduce its sale team, which is currently at 13, to about 10.3. Now, let's not worry about the practicality of this. How are you going to have a sales team of 10.3? You can either have 10 or 11, right? So let's not worry about that. Let's say that input 1 is reduced from 300,000 to 237,540. Input 2 is reduced from 13 to 10.3, right? There are practical ways of arguing that way. So you are going to say that if you really want to argue 10.3 in terms of number of people in the team, you are going to say that there are going to be 10 sales people who are going to be working on DMU1 full time, and the 11th salesperson is only going to spend 30% of her time for DMU1, right? That is to explain 10.3, right? So things can be explained. But the idea is not to get into the semantics of this. Idea is to get the idea that DMU1 can be called efficient only if it reduces the input, and now we have quantified that reduction. It needs to reduce the budget from 3 lakhs to about 2,37,000, and it needs to reduce the team size from current value of 13 to about 10.3. But this was graphical explanation. Point of intersection, draw two lines, you know the equation of the two lines because you know the coordinates of 2 points passing through the two lines through which the line passes. This was a very geometric explanation. Is there a more mathematical explanation? Can we actually use the optimization problem that we had solved for DMU1? Remember, in all this explanation, when we identified 2,37,000 and 10.3, we have not used the optimization problem. Can we use the solution of the optimization problem for DMU1 in identifying this HCU? Answer is obviously yes. So how are we going to calculate that? Recall that the solution for the optimization problem for DMU1 had an objective function value of 0.792. Therefore, we call DMU1 as inefficient. Let me show you that on Excel. So, okay, if you recall, this was the solution for the optimization problem for DMU1. Okay. Why DMU1? Okay, because I am using output weights, input weights for DMU1, normalizing the input for DMU1, normalizing the input for DMU1. So I know that this is the solution for the optimization problem for DMU1. So what was the reported objective function? The reported objective function was 0.79, which is why we called DMU1 as inefficient DMU. Look at DMU2. When DMU2 solved its problem, it reported an objective function value of 1. Therefore, DMU2 was efficient. So DMU1 reported a efficiency of 0.79. Now what we are going to do is, we are going to look at the dual solution for this linear programming problem. What do I mean by dual solution? Again, I refer you to the session that we had on operations research and particularly linear programming problems. From those sessions, you know what the dual of the linear programming problem is. So, you also know how to find the dual solution from the solution of the primal problem. You know that, right? So, let me just show you that for DMU1. So, this is the linear programming problem solved by DMU1. So, this is our primal, right? This is essentially our primal. So, this is primal. Now, if you were to formulate the dual of this linear programming problem, we have already shown that this is the linear programming problem, right? No question about that. So, if we were to find the dual of this linear programming problem and we would have solved that dual linear programming problem, we would have obtained the dual variables. How do you find the solution to the dual variable, to the dual problem from Excel? You run what is called as sensitivity. How do you get sensitivity in Excel? So let me show you that very quickly. I have already solved this problem, right? So this problem should already be there, already formulated. Now if I hit the solve button, I will ask for sensitivity report. And hit OK. Okay, let me do that. Sensitivity report will get published by Excel. So Excel publishes sensitivity report on demand. It is not auto-generated. We have to ask for it. Okay, we have to ask for it. Okay, what do I understand from this sensitivity report? Okay, let's not. So these are the values. These are the values of your input weights and output weights. 2.06, 10 to the power of negative 6. 2.06, 10 to the power of negative 6, 0.02923, 0.0293, 7.91, right, 7.91, 10 to the power of negative 7, 7.91, 10 to the power of negative 7. All these are your primal values, your primal decision variables, right? The x's and y's from the original DEA formulation, right? Now you look at the bottom table and look for what are called as shadow prices. Now, shadow prices are the values of your dual variable. Now, what was H9? What was H9? H9, okay, H9 was our, or H9 represent this equation represents the normalization of input, and you can see that it is a tight constraint, right? It is a tight constraint. Left hand side is 1, right hand side is 1, right? It's a tight constraint. The dual variable corresponding to that is our objective function, 0.7919. 0.7919 is our objective function. Okay, the dual variable corresponding to the input normalization constraint. Look at all the other all the other dual variables, all the other dual variables are 0 except for these two. So now you have a dual variable 0.74, the other dual variable is 0.259. Now what is this dual variable corresponding to? This dual variable is corresponding to the cell H12. What was H12? H12 was this constraint. Now what was this constraint for, right? Remember what was this constraint for? This was a constraint for DMU1, this was a constraint for DMU2, this was a constraint for DMU3, this was a constraint for DMU4, this was a constraint for DMU5. What was the first constraint? The first constraint was using the input and output weights of DMU1, DMU1 should not get an efficiency more than 1. What was this constraint? This constraint said that using the input and output weights of DMU1, DMU2 should not get an efficiency more than 1. Similarly, using the input and output weights of DMU1, DMU3 should not get an efficiency of more than 1. Similarly, this constraint said that using the input and output weights of DMU1, DMU4 should not get an efficiency of more than 1. This constraint said that using the input and output weights of DMU1, DMU5 should not report an efficiency of more than 1. So now there are only two dual variables which are non-zero. Right, this was the dual variable for the normalization constraint. That we have already explained. Now, out of these inequalities, these are all inequalities. Out of these 5 inequalities, there are only two dual variables which are non-zero. One corresponds to H12. H12 corresponds to DMU2. H12 corresponds to DMU2. And this dual variable is also non-zero, and that corresponds to H15. H15 corresponds to DMU5. Therefore, DMU2, let us highlight that, DMU2 and DMU5 are the only two DMUs and correspondingly only two constraints for which the dual variable is non-zero. 0.74 for the first and 0.259 for the second. This dual variable is 0, this dual variable value is 0, this dual variable value is 0. Okay. Therefore, we are going to conclude that for DMU1, DMUs 2 and 5 are the reference unit. For DMU1, DMUs 2 and 5 are the reference unit. Why did we conclude that? We simply looked at the dual variable values, and these are the only non-zero dual variable values, 0.74 and 0.259. 0.74 corresponds to the dual dual variable corresponding to constraint number 2, which was for DMU number 2, and 0.259 corresponds to the constraint constraint number 5, which corresponds to the DMU number 5. Therefore, for DMU1, DMU2 and 5 are the reference units. I hope that is understood. Now, from this optimization problem solution and these values of the dual variables, we are going to carry the dual variable values which are non-zero. 0.74 and 0.259. 0.74 and 0.259. 0.74 corresponds to the DMU2 and 0.259 corresponds to DMU, not SMU, DMU5. Okay. Now we have identified the reference unit, which is what we wanted. No, we in our geometric calculations, that's what we did. We identified first of all which are the reference units. And then we simply use geometry to find the point of intersection. So far we have reached this point using optimization. Now let us find the coordinates of HCU using optimization. In particular, we are going to use the dual variable values 0.74 and 0.259. Okay, so let us go back to PPT and see these calculations already done for you. Let me load the PPT. Okay, so we have seen the geometric solution to identify the coordinates of HCU. Now we have the dual variable values obtained from the optimization problem for the inefficient DMUs. We are going to use those dual variable values to identify the coordinates of HCU for DMU1. Already done for DMU1 using geometry. Let us do that using analytical method. Okay. So what we are going to do is, we are going to use what are called as shadow prices, and we realize that there are only two dual variables which are non-zero for the inequalities. And those dual variables correspond to the DMU2 and DMU5, and therefore we conclude that those are our reference units for DMU1. The dual variable values that we are carrying forward from that optimization solution was 0.74, which corresponded to DMU2, and 0.259. I have rounded that off. 0.259 has been written as 0.26, which corresponded to the DMU5. Okay, now let us see the calculations. Let us use these dual variable values. What are we interested in finding? We are interested in finding the coordinates of HCU. Now you will be able to understand why this was called composite unit. Okay, for that, just like we did that for the geometric unit, for the geometric method, we are going to require the coordinates of 2 and 5, which are the reference units. Okay, so now these are the coordinates of the reference units. These are the coordinates of the reference unit 2. These are the coordinates of the reference unit 5. You can verify that from the data, which essentially means that DMU2, which is an efficient DMU, is consuming a budget of 256,000 and a team size of 9 to generate a sales of 10 lakhs. Similarly, DMU5 is spending only 185,000 budget, larger team size of about 14 people, and it is finding itself on efficiency frontier. Now these are the two reference units for DMU1. Okay, what are the dual variables corresponding to the reference units? For the reference unit 2, the dual variable value was 0.74. For the reference unit 5, the dual variable value was 0.26. This comes from the shadow prices which we just saw in the Excel. Now we are going to multiply this 0.74 with the coordinates of 2. What is the output coordinate of 2? Output coordinate, every DMU generates a sales of 10 lakh rupees. So that is the output coordinate. So 10 lakh rupees into 0.74 plus 10 lakh rupees into 0.26 will give you the output coordinate of the hypothetical composite unit, right? And you realize that 0.74 plus 0.26, this plus this is actually 1. This plus this is actually 1, and therefore 10 lakhs into 0.74 plus 10 lakhs into 0.26 is going to return the same 10 lakhs. What is the implication? We are saying that when DMU1 wants to be called as efficient DMU, it still has to report a sales of 10 lakhs. That is what we mean by this. Now the budget coordinate of DMU2, that was 256,000. 256,000 multiplied by the dual variable 0.74 plus the budget coordinate of reference unit 5, which was 185,000, multiplied by the dual variable value of 5, which is 0.26. So 256,000 plus 0.74 plus 185,000 into 0.26 is going to give you 237,540. Okay, that should be the budget coordinate for hypothetical composite unit for 1. Similarly, how do you identify the team size for HCU1? Team size for HCU1 is going to be identified by taking the team size for 2, which is 9 here, multiplying that by the dual variable 0.74, team size of 5, which is here, dual variable of 5, which is here, and you are going to get 10.3, which is the required team size for HCU1. So, you notice that this is the same solution that we had identified using the geometric method. This method did not use optimization. This method simply said, I know the equation of two lines, find the point of intersection of the two lines, and using simple geometry, we identified 237,540 to be the budget and 10.3 to be the team size. Now we have obtained the same values using an optimization logic, using the optimization argument, particularly using the dual variable values. Okay, so what is our policy prescription? The policy prescription is the same, right? If DMU1 wants to be called efficient, it needs to generate a sale of 10 lakh. It needs to use a budget of 237,540. It is going to need a team size of 10.3 only. What is the current spend? Currently, DMU1 is spending 3 lakhs. Currently, DMU1 is having a team size of 13, and using these two inputs, it is able to generate an output of 10 lakhs. So what is our recommendation for DMU1? Our recommendation for DMU1 is to bring down the budget by about 62,000, reduce the team size by about 2.7, and then you will become efficient. Okay, understood? Let us conclude the session by doing the same analysis for DMU4. Recall what is the argument for DMU4? DMU4 is inefficient. Our recommendation is it moves along the blue dotted line and comes here. Once again, you can solve this problem geometrically. Point of intersection. Blue dotted line and solid red line are intersecting at that HCU4, and therefore finding the coordinates of HCU4 is easy geometrically. But you realize that this geometry is easy when you have a nice two-dimensional plot like what we have on the slide here, where we only had two inputs, we only had one output, and that output was fixed. We are not going to have this kind of luxury of this easy calculations in reality. In reality, you are going to have multiple inputs, multiple outputs, and therefore we cannot really rely on the graphical method. We cannot really rely on the geometry. So let us do the same calculations, but instead of using geometry, let us use optimization, okay, and calculate the coordinates of HCU4. Because we saw when we use the dual variable and the reference units, we really don't need geometry. Okay, so let us do that. Let us go to Excel first. Let us look at the DMU4. Why was DMU4 inefficient? DMU4 was inefficient because when it solved its own DEA, linear programming DEA, it reported an objective function of 0.84. Therefore, DMU4 is inefficient. Now, once again, let us run the sensitivity. Let us get the sensitivity report for DMU4. You have already seen how to get that sensitivity report. I already have that generated for you. I am not going to do that again. Right. So, this is the sensitivity report for DMU4. Make sure that it matches. What is the input weight? 6.21 10 to the power of negative 7. 6.21 10 to the power of negative 7. Right. You think this is a different number? Right. So same number. They are not different numbers. This is second input weight is 0.075. 0.075. The output weight is 8.4 10 to the power of negative 7. 8.4 10 to the power of negative 7. Right, so it is the same solution. So this is the sensitivity report for DMU4. This is not of interest to us, right? We have already seen that. This is of less importance to us because I can already get the final value of the decision variables from here. This is the primal decision variables. Now we are interested in finding the decision variables of the dual, which are called shadow prices in Excel. Okay, shadow prices in Excel. What does this 0.84 corresponds to? 0.84 corresponds to H9. H9 is our normalization of input. H9 is our normalization of input. So the dual variable corresponding to the normalization of inputs is our objective function value, 0.84. 0.84. Now out of the inequalities, this was an equality, normalization of input was an equality. Out of the inequalities, there are going to be 5 inequalities, one corresponding to each of the DMUs. One corresponding to each of the DMUs, right? So I am not going to repeat what each of these inequalities correspond to. They are essentially saying that using the input and output weights of DMU4, none of the DMUs should report an efficiency of more than 1. Okay, for these 5 inequalities, these are the only two dual variables. These are the only two dual variables which are non-zero. Other than that, this is 0, this is 0, this is 0. This 0.7 corresponds to H12. What is H12? H12 in this. H12 is this. So this is the DMU. Similarly, 0.29 is the dual variable corresponding to the constraint H13. H13 corresponds to which DMU? H13 corresponds to DMU3. H13 corresponds to DMU3. Therefore, we are going to conclude that for DMU4, first of all, we are going to conclude that DMU4 is an inefficient DMU. For DMU4, DMU2 and 3 are reference units. DMU2 and 3 are reference units. DMU2 and 3 are reference units. Now using the same method that we had employed for DMU1, we are going to calculate the coordinates of HCU for DMU4. Let us quickly check what the dual variables are. Dual variables are 0.74 and 0.295. If you notice, if you add up, if you say this plus this, it is going to add up to 1, just like it added up for this, right? This was also 0.74 plus 0.259 was 1. Okay, it is going to add up to 1 always. Okay. Now 0.74 and 0.295 are the dual variables. We are going to take it for our calculation. Let us go to Excel again. Let us go to PPT again. This time we are interested in finding the coordinates of HCU4. We already identified that for DMU4, DMU2 and DMU3 were the reference units. From the data that was earlier given to you, you can verify that for DMU2, the coordinates were 256 and 9. Well, you need not have to go to the original data. You could see that from here itself. For DMU2, these are the coordinates. For DMU3 was spending a budget of 5 lakhs. It was using a team of 7 people and it was generating a sales of 10 lakhs. Right. So those were the coordinates of 3. What were the dual variable values corresponding to 2? Dual variable value corresponding to 2 was 0.705. Dual variable corresponding to 3 was 0.295. Now, same calculations. 10 lakhs is the sales for DMU2. Multiply that by the dual variable value 0.705. The sales for DMU3 was 10 lakhs. The dual variable is 0.295. 10 lakhs multiplied by 0.705 plus 10 lakhs multiplied by 0.295 is going to give you 10 lakhs, which is the output, which is sales. The budget 256,000 for DMU2 multiplied by the dual variable for DMU2 plus the budget for DMU3 and the dual variable value for DMU3. So 256,000 multiplied by 0.7 plus 500,000 multiplied by 295 is going to give you this value 327,980. Similarly, the team size 9, 9, multiplied by the dual variable value, 7 multiplied by the dual variable value is going to give you the coordinates of HCU4. So using the dual variable values, you are going to calculate the coordinates of HCU4. Using the dual variable values, you are going to calculate the coordinates of HCU4. So what are the coordinates of HCU4? Let us go and look at that in. So what are the coordinates? Apparently this is 327,000 something, 980, and the team size was, I think, 8.4. What does that mean? That means if you draw a vertical line, this is going to be that 327,000, and if you draw the horizontal line, it is going to sit just above 8, 8.4. Okay, this is going to be the coordinates of HCU4. So how should DMU4 become efficient? DMU4 should become efficient by spending a budget of about 327,000, using a team size of about 8.41. But what is it doing currently? Currently it is spending a budget of 3,90,000. It is using a team size of 10. So what is our recommendation? What is our recommendation for DMU4? Our recommendation for DMU4 is to reduce the budget by 62,000 and reduce the team size by about 1.6. If it does that, it is going to move from its current location. Along the blue line, and it is going to sit on that red efficiency envelope, and then anybody will be forced to call DMU4 also as efficient DMU, because at that time it would be sitting on an efficiency frontier. That is how you prescribe action items for inefficient DMUs so that they can become efficient DMUs. What is the key? Key here is to use the dual variable values that can be obtained by solving the optimization problem. Okay, we saw that geometry can help, but geometry can help only in simple examples like the one that is presented here. More generically, we are going to use the dual variable values to find the coordinates of the hypothetical composite unit. Once again, to highlight why was that called hypothetical composite unit? It was called composite unit because it is composed of 2 and 3, right? We used 70% of 2, 29% of 3, and we got the hypothetical composite unit for 4. Here we used 74% of DMU2, 26% of DMU5, and we got the hypothetical composite unit for 1. That's why it is called a composite unit. It consists of 2 efficient DMUs. Okay. One last comment before we end. Where can we use DMUs or DEA? Where can we use data envelopment analysis? Data envelopment analysis, fairly obvious, can be used when we have data about various decision making units and we want to find which of these decision making units are efficient, which are not efficient. So let me spend last 1 minute in self promotion. I hope you don't mind me promoting myself. We did an analysis, and I am showing you an article that we wrote some time ago, where we looked at Manrega implementation. Manrega is the Rural Employment Guarantee Scheme. We looked at the Rural Guarantee Scheme and looked at various states that tried to implement Manrega. So they have various inputs, they have various outputs, and we looked at which state is efficiently implementing Manrega, which state is not efficiently implementing Manrega. This was all done using publicly available data, and we used DEA and found out which states are efficient, which states are non-efficient. More importantly, we were able to have policy prescription for states that were found to be inefficient, and we were able to tell them what they should be doing so that they can also be called as efficient states implementing Manrega. So with that concluding remark, let me end the session. Thank you.